Welcome to all in the lecture series of functional analysis. Now in this lecture we see linear space L infinity of bounded sequence is a Banach space under the norm defined by norm of x equals to supremum of mod of xi I. Supremum varies over I, where x equals to the sequence xi I is from 1 to infinity be any element of L infinity, where each coordinate xi I is either real or complex. Now here we have to show that linear space L infinity is a Banach space. To see it, firstly we see what is the linear space L infinity. Now here in the statement we say that linear space L infinity of bounded sequence. That means any element x belongs to L infinity is a sequence. That means each element of L infinity, it is written in the form of sequence xi1, xi2, its ith coordinate is xi I and so on, where each xi I is either real or complex. Also here we say that each element is a bounded sequence. That means here for each I mod of xi I, it is less than or equals to Cx, where Cx is something a fixed real number and this Cx is depending on this x, we can write it here Cx. This Cx is depending on this x but does not depending on this xi I. That means for any term xi I, mod of xi I is lesser than or equals to Cx. And hence we say that the sequence x is a bounded sequence which is the element of L infinity. Now after this we show that the linear space L infinity of bounded sequence is a Banach space. To prove it, firstly we prove that the linear space L infinity is a norm space with the norm defined as norm of x equals to supremum over I mod of xi I. So firstly we will show that linear space L infinity is a norm space with the norm defined by this norm of x equals to supremum over I mod of xi I. That means firstly we have to verify the first axiom of the norm, and first axiom of the norm is norm of x, it is always greater than or equals to 0 for any x belongs to the element of L infinity. Now here as x be the element of L infinity, therefore x is a bounded sequence. That means x equals to the sequence xi I is from 1 to infinity, where each xi I is either real or complex for all I. Now here x belongs to L infinity and therefore here norm of x, by using this definition, it is equals to the supremum over I mod of xi I. Now here each xi I is either real or complex and therefore mod of xi I, that is the absolute value of xi I, it is always greater than or equals to 0. That means for all I, mod of xi I, it is always greater than or equals to 0, and as for each I, mod of xi I greater than or equals to 0, therefore its supremum, that means supremum over I mod of xi I, that is also greater than or equals to 0, and it implies that this is greater than or equals to 0. That means for any element of L infinity, its norm is always greater than or equals to 0, and therefore the first property of a norm is satisfied. Now the second property of the norm, N2. In N2 we have to show that norm of x equals to 0 if and only if x equals to 0. So we start with norm of x equals to 0. Now norm of x equals to 0 implies that we write down the definition of norm of x equals to the supremum over I mod of xi I, that is equals to 0. Now it is the supremum taken over I. It is the supremum of mod of xi I, where each xi I is real or complex, and as it is the absolute value, therefore, and it is the absolute value, and as its supremum equals to 0, supremum equals to 0 and each term is non-negative, therefore the supremum equals to 0 implies that each mod of xi I equals to 0 for all I, because here we are taking the supremum of absolute values of xi I, and as it is the absolute values of xi I, that means this term is non-negative, and the supremum of non-negative term is 0, that means each term must be 0, and as absolute value equals to 0, it implies that xi I equals to 0 for all I, and for each I, xi I equals to 0 implies that x is equals to the sequence xi1, xi2, ith term is xi I, and so on. Each term is 0, and therefore we are getting that x equals to 0. Now conversely, we start with the x equals to 0. X equals to 0, that means each coordinate must be 0, and therefore it implies that xi I equals to 0 for all I. As xi I equals to 0 for all I, it implies that its absolute value it is also equals to 0 for each I, and absolute value it is equals to 0 for every I, therefore supremum is also equals to 0, and supremum is 0 means norm of x equals to 0, and therefore in both cases we get that norm of x equals to 0 if and only if x equals to 0, and therefore the second property of a norm is also here satisfied. Now we come to the third property of the norm, and the third property of the norm is that norm of x plus y, that is lesser than or equals to norm of x plus norm of y. Here we have to prove the triangle inequality. So we start with any two elements of L infinity. We consider let x equals to the sequence xi I is from 1 to infinity with the element of L infinity, and y equals to the sequence eta I is from 1 to infinity is the another element of L infinity. Now here therefore we consider the norm of x plus y. It is equals to, as here when we are taking x equals to the sequence xi I, then its norm becomes norm of x equals to the supremum over I mod of xi I. In the similar way, norm of x plus y, it is equals to the supremum over I mod of xi I plus eta I. Now here each xi I and eta I both are the elements of R or C, and therefore mod of xi I plus eta I, it is always lesser than or equals to mod of xi I plus mod of eta I for all I. Using this here we write down it is lesser than or equals to supremum over I mod of xi I plus mod of eta I. And now we separate the supremum, and it is equals to supremum over I mod of xi I plus supremum over I mod of eta I. And it is nothing but norm of x plus norm of y. That means here we get that norm of x plus y, it is lesser than or equals to norm of x plus norm of y. That means the third property of a norm is also satisfied. Now we have to prove the last property of a norm, that is the norm of alpha x, it is equals to mod alpha into norm of x. in the fourth property, we have to show that norm of alpha x, that is equals to mod alpha into norm of x, where alpha be any scalar. Now here we start with norm of alpha x. By using this definition, it is equals to supremum over I mod of, now here x equals to the sequence I, then we are taking norm of x equals to supremum over I mod of xi. In the similar way, here we have norm of alpha x, and that is equals to supremum over I mod of alpha xi. Now here alpha is independent of this I, and this supremum is taken over all I, and therefore we can write it as supremum over I mod alpha into mod of xi. Now in the next step we can take mod alpha out, that means it is equals to mod alpha into supremum over I mod of xi, and it is equals to mod alpha into norm of x. That means norm of alpha x, it is equals to mod alpha into norm of x, and in this way the fourth property of a norm is also satisfied, and therefore the norm defined like this, norm of x equals to supremum over I mod of xi, is a norm on L infinity, and therefore L infinity with this norm is a non-linear space. Therefore the linear space L infinity of bounded sequence becomes a non-linear space. Show that the sequence space L infinity is a complete metric space. That means we have to show that every Cauchy sequence in L infinity converges in L infinity. So we consider the Cauchy sequence. Let sequence xn be any Cauchy sequence, in L infinity. As it is a Cauchy sequence in L infinity, that means for each I, xn is the element of L infinity, and L infinity it is called as a linear space of bounded sequence. That means each element of L infinity is a sequence, and therefore this xn is written in the form of a sequence as xi1, xi2, its ith coordinate is xi I, and so on, where each xi I is either real or complex. Now corresponding to this n, we write down here xi1n, xi2n, xi and so on. Now here, as it is a Cauchy sequence in L infinity, and we have to show that the linear space L infinity is complete, that means we have to show that this Cauchy sequence in L infinity converges in L infinity. That means we have to show that xm converges to some x, where x is the element of L infinity as m goes to infinity. That is we have to show. To prove this, we start with the epsilon. We take some epsilon. Let epsilon greater than 0 be given. Then for this epsilon, as it is a Cauchy sequence in L infinity, therefore for the given epsilon, greater than 0, there exists a natural number n naught such that for all m comma n greater than or equals to n naught, d of xm comma xn, that is equals to norm of xm minus xn, it is lesser than epsilon. Now we write down the value of norm of xm minus xn as, that is norm of xm minus xn, it is equals to supremum varies over I mod of xi im minus xi n. It is lesser than epsilon whenever m and n greater than or equals to n naught. Now here the supremum varies over I mod of xi im minus xi n, that is lesser than epsilon. That means the supremum is lesser than epsilon, and therefore the individual term, that is mod of xi im minus xi n for each I, which is always lesser than or equals to the supremum, mod of xi im minus xi n, and it is lesser than epsilon whenever m comma n greater than or equals to n naught. And it is true for each I, for each fixed I. For each fixed I, mod of xi im minus xi n, which is lesser than or equals to supremum, and supremum is lesser than epsilon whenever m and n greater than or equals to n naught. And it implies that for each fixed I, mod of xi im minus xi n, it is lesser than epsilon for all m comma n greater than or equals to n naught. We read it like this. For a given epsilon greater than 0, there exists a natural number n naught such that for all m comma n greater than or equals to n naught, mod of xi im minus xi n, that is lesser than epsilon, and it is nothing but the definition of a Cauchy sequence, and hence we say that for each fixed I, sequence xi im is a Cauchy sequence. Now in this sequence, each term is either real or complex, and therefore it is a Cauchy sequence in R or C. And we know that both R and C both are complete. Therefore, every Cauchy sequence in R and C converges in R and C. And therefore, for this Cauchy sequence xi im, which is a Cauchy sequence in R or C, and R and C both are complete. Therefore, xi im converges to some xi I as m goes to infinity, and it is true for each fixed I. That means for each fixed I, xi im converges to xi I as m goes to infinity. That means we write it like this, that is xi 1 m converges to xi 1, where xi 1 is element of R or C. Xi 2 m converges to xi 2, it is again element of R or C, and so on. The ith coordinate is, ith terms are xi I. Xi im converges to xi I, and it is again either the element of R or C, and so on. Now, using all these limits, collecting these limits, we write down x equals to the sequence xi 1, xi 2, xi I, and so on. Now here we get x equals to the sequence xi 1, xi 2 up to xi I, and so on. Now here we have to show that our Cauchy sequence xm that converges to this x and x is the element of L infinity. That is we have to show now. For this, norm of xm minus x, norm of xm minus x, it is equals to, as xm equals to the sequence xi im, I is from 1 to infinity, x equals to the sequence xi I is from 1 to infinity, therefore, and norm of x, it is equals to the supremum over I mod of xi I. In the same way, we define norm of xm minus x, that is equals to supremum over I mod of xi im minus xi I. Now here, as we know that as m goes to infinity, xi im converges to xi I for all I. As we see, xi im converges to xi I for all I. That means xi im minus xi I, that goes to 0 as m goes to infinity, and it is true for all I, and therefore as it goes to 0 for each I, therefore the supremum over I mod of xi im minus xi I, that also converges to 0 as m goes to infinity. That is norm of xm minus x goes to 0 as m goes to infinity, and it implies that xm minus x converges to 0 as m goes to infinity, that is xm converges to x as m goes to infinity. In this way, we show that our Cauchy sequence xm in L infinity converges to this x. Now we have to show that this x, that is equals to the xi1, xi2, xi and so on, it is the element of L infinity. To show that x is the element of L infinity, and as we see in the definition of L infinity, that every element of L infinity is a bounded sequence. That means here we have to show that x equals to the sequence xi, it is a bounded sequence. That means here we have to show that each coordinate of the sequence x, it is lesser than something a fixed real number. X equals to the sequence xi, I is from 1 to infinity. Now here we show that x is a bounded sequence. That means we have to show that for each I, mod of xi is something a fixed real number, say k. That is we have to show. For this we start with mod of xi. It is written as mod of xi minus xi m plus xi m. Just add and subtract xi m. It is lesser than or equals to mod of xi minus xi m plus mod of xi m. We give it the equation number 1. As we know that the sequence xi m, it is equals to the sequence xm, and it is the element of L infinity. Xm is the element of L infinity. That means this is a bounded sequence. It is a bounded sequence means for each I, mod of xi m, it is lesser than something a fixed real number, and therefore we say that mod of xi m, it is lesser than km, where km greater than 0 is something a fixed real number. Also here, as we prove that for each I, xi m converges to xi I as m goes to infinity. We write it in the form of epsilon as mod of xi m minus xi I, that is lesser than epsilon for all m greater than or equals to n naught. And therefore, using these two inequality, we write down the equation 1 as mod of xi I, that is lesser than or equals to mod of xi I minus xi im plus xi im. And now it is lesser than xi I minus xi im, it is lesser than epsilon, plus mod of xi im, that is lesser than km for all m greater than or equals to n naught. It implies that for each I, mod of xi I, it is lesser than epsilon plus km. It is nothing but something of fixed real number. That means for each I, mod of xi I is lesser than something of fixed real number. It implies that x equals to the sequence xi I is from 1 to infinity. It is a bounded sequence, and as it is a bounded sequence, therefore x be the element of L infinity. We start with the Cauchy sequence xm in L infinity. Using this Cauchy sequence, we get the element x. We start with the Cauchy sequence xm in L infinity, which is a Cauchy sequence in L infinity. For this Cauchy sequence, we get the element x, that is equals to the sequence xi I, such that xm converges to x and x is the element of L infinity as m goes to infinity, where sequence xm be any arbitrary Cauchy sequence in L infinity. It implies that every Cauchy sequence in L infinity converges in L infinity, and therefore the linear space L infinity becomes a complete metric space. That means linear space L infinity is a complete metric space. Also we prove that it is a norm space, and hence we say that linear space L infinity is a complete norm linear space. That means the linear space L infinity is Banach space. Under the norm of x equals to supremum over I mod of xi I, where x equals to the sequence xi I is from 1 to infinity with the element of L infinity. In this way, we show that the linear space L infinity is a Banach space. This is the example of the Banach space.